In the last decade, over 15,000 Burmese pythons have been removed from Florida's Everglades. But recently, wildlife biologists discovered something that stopped them cold. Hundreds of these massive constrictors, some measuring over 15 feet long, were turning up dead with their heads cleanly severed from their bodies. No human tools, no signs of trapping equipment. Something in the swamps was hunting the hunters. For years, scientists believed these apex predators were virtually invincible in their adopted home, capable of swallowing deer whole and growing to lengths that rivaled the largest snakes ever recorded in North America. The python invasion represented one of the most catastrophic ecological collapses in modern American history, with mammal populations in some areas declining by more than 99%. Every conventional method of control had failed or fallen short. But now, something had changed. Something was fighting back. And when researchers finally identified the culprit, it challenged everything ecologists thought they understood about invasive species dynamics and the hidden resilience of damaged ecosystems. This is the story of a discovery that may rewrite the playbook on how nature responds to biological invasions. Stay with us until the end, because what scientists found has implications far beyond Florida. If you're fascinated by wildlife mysteries and want to understand how ecosystems actually fight back against catastrophic change, hit that like button and subscribe, because we're diving deep into one of the most surprising ecological stories of the decade. The Florida python, how thousands of Burmese python got recently decapitated. Let's be clear about what we're dealing with here. The headline sounds like sensationalist clickbait. Thousands of decapitated pythons? Scientists shocked? It reads like a creature feature, not peer-reviewed science. But strip away the dramatic framing, and what remains is a genuine ecological mystery that has forced wildlife biologists to reconsider fundamental assumptions about invasive species management. The discovery didn't happen all at once. It emerged gradually through the accumulated observations of python hunters, wildlife officers, and research scientists working in the vast wetland wilderness of South Florida. Individual reports came first. A hunter would find a dead python, headless, with no obvious signs of human involvement. Then another, then clusters of them. By the time patterns became undeniable, the phenomenon had already been occurring for years, hidden in the labyrinthine waterways where few humans venture, and fewer still look closely at dead snakes. Florida has become the unintended laboratory for one of the most dramatic invasive species experiments ever conducted. The state hosts more non-native reptile and amphibian species than anywhere else in the continental United States. Climate, habitat diversity, international trade routes, and decades of poorly regulated exotic pet commerce have transformed the peninsula into a real-time demonstration of ecological disruption. But the Burmese python invasion stands apart. These snakes didn't just establish themselves, they didn't merely survive, they exploded into dominance with a speed and thoroughness that blindsided conservation biologists who thought they'd seen everything. Within 2 decades, an animal that had no business existing in North America had effectively restructured the entire food web of one of the continent's most unique ecosystems. The decapitation phenomenon matters because it suggests something profound. For years, the narrative around Florida's pythons was one of irreversible catastrophe, of an ecosystem pushed past a tipping point from which it could never recover. Native wildlife was disappearing. Traditional predators couldn't compete. Human intervention, despite millions of dollars and thousands of hours of effort, barely dented the python population. The snakes seemed unstoppable, and the Everglades appeared doomed to become a python-dominated wasteland where biodiversity went to die. But nature rarely reads the scripts we write for it. Ecosystems possess hidden mechanisms, dormant responses, and adaptive capacities that only reveal themselves under extreme pressure. The question that drove scientists to investigate these decapitations wasn't just what was killing the pythons, it was whether this represented a fundamental shift in the invasion dynamics, whether Florida's native ecology was mounting a counter-offensive that nobody predicted, and whether there were lessons here that could inform invasive species management worldwide. Burmese pythons are not native to Florida. They're not native to the Western Hemisphere. Their natural range extends across Southeast Asia, from eastern India through Indonesia, including Myanmar, Thailand, Vietnam, and southern China. These are tropical and subtropical snakes, adapted to monsoon forests, grasslands, marshes, and river valleys where wet and dry seasons create complex habitat mosaics. In their native range, Burmese pythons are impressive but not unchecked. They face predation as juveniles from birds of prey, large monitor lizards, and wild dogs. As adults, they compete with tigers, leopards, crocodiles, and other apex predators. Disease, parasites, and food scarcity limit their numbers. They're part of a balanced system that has evolved together for millions of years. The pathway to Florida was entirely human-made. The exotic pet trade exploded in the United States during the 1970s and 80s, fueled by growing interest in reptile keeping and minimal regulation of wildlife imports. Burmese pythons, with their striking patterns and relatively docile temperament as juveniles, became popular. Thousands were imported annually. Pet stores sold them cheaply, often to buyers who had no understanding of how large these animals would grow or how long they would live. A cute 2-foot hatchling becomes a 12-foot eating machine within a few years. Captive Burmese pythons can live 30 years or more. They require large, secure enclosures, specialized heating, and regular feeding of appropriately sized prey. Most owners were catastrophically unprepared. The release of unwanted pythons began in the late 1980s and accelerated through the 1990s. Some releases were intentional, owners who could no longer care for their pets dumping them in parks or wild areas. Some were accidental, escapes from inadequate enclosures during routine maintenance or following damage from storms. Hurricane Andrew in 1992 is widely considered a pivotal event. The Category 5 storm devastated South Florida, destroying numerous reptile breeding facilities and private collections. In the chaos, an unknown number of pythons and other exotic reptiles escaped into the surrounding environment. Whether this was the original founding population or merely supplemented an existing feral population remains debated, but genetic studies confirm that Florida's pythons descend from a relatively small number of founding individuals, suggesting a genetic bottleneck consistent with a limited release event or series of events in a concentrated time frame. South Florida turned out to be nearly perfect python habitat. The climate matches their native range. The Everglades and surrounding wetlands provide abundant water, cover, and prey. Winter temperatures rarely drop low enough to kill them, and the vast, roadless wilderness offers refuge from human detection. The first confirmed breeding population wasn't documented until the early 2000s, though scattered sightings occurred throughout the 90s. By the time scientists recognized a self-sustaining population existed, it was already too late for early eradication. The pythons had dispersed across hundreds of square miles of nearly inaccessible terrain. Population models suggest exponential growth began around 2003. Within a decade, estimates ranged from tens of thousands to over 100,000 individuals, though the true number remains unknown because these snakes are extraordinarily difficult to detect. Early warnings were absolutely issued, but they were largely ignored or underestimated. Herpetologists familiar with invasive reptiles in Florida predicted that tropical constrictors could establish wild populations if released in sufficient numbers. Papers published in the late 90s and early 2000s explicitly warned about the threat posed by large pythons. But predictions are different from reality, and the pace of the invasion caught everyone off guard.
Wildlife managers, already dealing with numerous invasive species in Florida, didn't prioritize pythons until evidence of ecological damage became overwhelming. By then, the window for containment had closed. The invasion had transitioned from preventable to manageable at best, and possibly to permanent. This pattern, where warnings precede action by years or decades, repeats across invasive species cases worldwide. The problem isn't lack of knowledge, it's the failure of institutions to act decisively on ecological threats until damage is already catastrophic.
The ecological impact of Burmese pythons on South Florida ecosystems ranks among the most severe documented invasive species effects anywhere. The data is staggering and unambiguous. Research published over the past 15 years has documented near-total collapse of mammal populations in areas of highest python density. In Everglades National Park, surveys comparing pre-invasion and post-invasion populations found that raccoons, which were once ubiquitous, had declined by 99.3%. Opossums declined by 98.9%. Bobcats, which once thrived in the park, decreased by 87.5%. Marsh rabbits and cottontail rabbits have become so rare in python-infested areas that they're functionally absent. White-tailed deer, though still present, have declined significantly. These aren't statistical anomalies or localized effects. These are ecosystem-wide collapses of entire taxonomic groups across hundreds of square miles. The mechanism is straightforward. Pythons are generalist predators with enormous size ranges and correspondingly broad prey preferences. Juveniles eat small mammals, birds, and lizards. Adults consume everything up to and including deer, alligators, and other pythons. They don't need to eat frequently. A large python can survive months between meals, meaning population control through starvation is essentially impossible. They hunt primarily by ambush, using heat-sensing pits along their jaws to detect warm-blooded prey in total darkness. Their ability to go long periods without food means they can persist at low prey densities that would starve most predators. This creates a predator pit scenario where prey populations are driven so low that recovery becomes impossible even if python numbers decline. The cascading effects extend far beyond direct predation. Birds that nest near the ground or in low vegetation have vanished from python-dense areas. Species like wood storks, roseate spoonbills, and various wading birds face increased nest predation. Juvenile alligators, once common, are now eaten in large numbers. The disruption of small mammal populations affects scavengers, secondary predators, and plants that depend on mammals for seed dispersal. Basically, the entire food web structure has been rewritten. Areas that once supported rich, diverse mammal communities now support almost none. The Everglades, already stressed by water management issues, agricultural runoff, and habitat fragmentation, couldn't absorb another major stressor. The python invasion pushed it past critical thresholds. Economic impacts are harder to quantify, but undeniably significant. Tourism in the Everglades depends partly on wildlife viewing. Fewer visible mammals mean diminished visitor experiences. Wildlife rehabilitation centers report increased cases of displaced or starving native predators that can no longer find prey. The state has spent tens of millions of dollars on python removal programs, research, and public awareness campaigns. Property values in some areas have been affected by python presence, particularly where residential areas border wild lands. Agricultural interests, while not the primary victim, report occasional losses of livestock and poultry to pythons. The long-term cost of ecological restoration, assuming it's even possible, will dwarf current expenditures. Are there any benefits? Scientifically documented benefits are minimal to non-existent.
Some have speculated that pythons might control invasive rodents or help suppress other invasive species, but evidence doesn't support this. The pythons don't preferentially target invasives. They eat whatever's available, and because native species evolved without python predation, they're often easier targets. There's no credible ecological role these snakes fill that wasn't already occupied by native predators like bobcats, panthers, alligators, and birds of prey. The suggestion that pythons provide some form of ecosystem service is not supported by peer-reviewed research. If anything, by removing native predators through competition and direct predation, pythons have eliminated animals that were providing legitimate ecological functions. The invasion represents pure loss, a subtractive event with no compensatory benefits to native biodiversity. One area where pythons have generated something resembling positive attention is in galvanizing public awareness about invasive species. The dramatic nature of the invasion, the striking appearance of the snakes, and the shocking scale of ecological damage have made pythons a poster child for the invasive species crisis. Educational programs, media coverage, and public engagement around the python issue have increased general understanding of how biological invasions work and why prevention matters. Whether this translates into meaningful policy change or behavioral shifts remains uncertain, but at minimum, the python invasion has demonstrated consequences in a way that abstract warnings never could. Still, this is cold comfort for an ecosystem that may never recover.
Several factors converged to make South Florida ideal for python proliferation. Climate is paramount. The subtropical to tropical conditions match the python's native range almost perfectly. Winter temperatures rarely drop below freezing for extended periods, and even cold snaps are typically brief. Pythons can tolerate short-term cold exposure by seeking shelter in burrows, under debris, or in other thermal refuges. The warm, humid summers provide optimal conditions for growth, digestion, and reproduction. Breeding occurs annually, with females capable of laying 20 to over 100 eggs, depending on size and condition. The long growing season means juveniles can reach reproductive size faster than they would in more temperate climates. Habitat structure also favors pythons. The Everglades is a vast mosaic of sawgrass marshes, tree islands, mangrove swamps, and hardwood hammocks, all interspersed with waterways and wet prairies. This complexity provides endless ambush sites, thermal refuges, and travel corridors. The water allows pythons to move efficiently and hunt aquatic and semi-aquatic prey. Vegetation provides cover from aerial detection, making visual surveys nearly useless. The sheer size of the region means that even intensive removal efforts cover only a tiny fraction of occupied habitat at any given time. Pythons are cryptic, nocturnal, and spend much of their time concealed. Detection rates are abysmal. Researchers estimate that even trained searchers find less than 1% of pythons present in a given area. The absence of native predators capable of controlling adult pythons is critical. Florida has alligators, which do occasionally kill and eat pythons, but alligators aren't specialized snake hunters, and large pythons are formidable opponents. Documented cases exist of pythons killing alligators and alligators killing pythons, resulting in mutual mortality. Florida panthers, the state's only native large cat, are critically endangered and number fewer than 200 individuals. They lack the population density to exert meaningful pressure on pythons. Birds of prey can take juvenile pythons, but adults quickly outgrow vulnerability to avian predation. There are no native mongooses, no large monitor lizards, no animals evolutionarily adapted to hunting large constrictors. The pythons entered an ecological vacuum at the apex predator level, and nothing was ready to challenge them.
Human factors continue enabling the invasion. Despite increased regulation, the exotic pet trade persists and releases still occur. Education campaigns have reduced but not eliminated the problem. Urban expansion pushes pythons into new habitats and creates edge zones where human-wildlife conflict increases. Roads facilitate python movement along canals and levees. Climate change is expanding the zone of thermal suitability northward, potentially opening new territory for python colonization. Modeling studies suggest that without sustained cold winters, pythons could eventually establish across the entire Gulf Coast and into the southeast. Each warm winter extends their range slightly and increases survival rates of northern outliers. But nature isn't entirely defenseless. Emerging evidence suggests that some native species are adapting. Alligators in python-dense areas show altered behavior, potentially becoming more aggressive toward snakes. Some mammal populations that haven't been entirely extirpated may be developing behavioral avoidance strategies, though evidence here is preliminary. Disease represents a potential natural check. Pythons in Florida have been documented with various pathogens, including parasites and fungal infections. Whether these will develop into population-limiting factors remains unknown. In their native range, Burmese pythons are regulated partly by disease, and isolated populations without exposure to diverse pathogens sometimes experience die-offs when novel diseases emerge. Climate extremes can also impose limits. While Florida's climate generally favors pythons, severe cold events still occur. The winter of 2010 saw temperatures drop into the 20s Fahrenheit across much of South Florida, and wildlife officers reported finding dead and dying pythons. These events are rare but consequential. If climate change paradoxically increases the frequency of extreme weather variability, cold snaps could occasionally knock back python populations in marginal habitats. Hurricanes also affect pythons. Storm surge, flooding, and habitat destruction can kill snakes directly or disrupt breeding. However, pythons are hardy, and survivors rebound quickly when conditions improve. And then there's the decapitation phenomenon. Early theories ranged from the plausible to the bizarre. Some speculated that a serial animal killer was targeting pythons. Others suggested rival pythons were fighting, though pythons rarely kill each other in such specific ways. Alligators became early suspects, but the wound patterns didn't match alligator dentition or feeding behavior. Alligators crush and tear. These snakes were cleanly severed. Another theory proposed that boats or machinery were striking pythons crossing waterways, but the consistency of the wounds and the locations of the bodies didn't fit accidental strikes. The mystery deepened because the decapitations occurred across wide geographic areas in remote locations rarely accessed by humans or machinery. Something systematic was happening, and scientists had no ready explanation. The answer, when it finally emerged, came from careful field observation, necropsy data, and an understanding of predator behavior that most biologists had overlooked.
To understand what could kill an adult Burmese python, you first need to understand what makes these snakes such effective predators. They're not venomous, they don't inject toxins. They kill through constriction, applying overwhelming mechanical force that stops blood flow and prevents breathing. When a python strikes, it happens in a fraction of a second. The snake detects prey using a combination of vision, scent, and infrared sensing through specialized pits. Once prey is within range, the python lunges, mouth open, and grabs with needle-sharp, backward-curving teeth. The teeth don't chew or tear, they hold. The instant the python secures a grip, its body coils around the prey in rapid, powerful loops. Constriction is often misunderstood. Pythons don't crush bones or squeeze until organs rupture. What they do is far more elegant and efficient. Each time the prey exhales or its heart beats, the python tightens slightly. The prey can't inhale fully. Blood pressure drops as vessels are compressed. Within minutes, the prey loses consciousness. Death follows quickly.
The process is highly energy efficient, allowing pythons to subdue animals much larger than themselves with minimal risk of injury. A 15-foot python can kill a full-grown deer. The constriction is so powerful that struggling is often futile. Prey that fights exhausts itself faster, accelerating its own demise.
After the kill, pythons face the challenge of consumption. Their jaws are connected by elastic ligaments, allowing the mouth to open to extraordinary widths. They don't dislocate their jaws, a common misconception. Instead, the jaw structure is loosely articulated, and the lower jaw halves can move independently, allowing the snake to walk its mouth over prey much wider than its head. Swallowing is slow. A large meal can take hours. The snake uses rhythmic muscular contractions to gradually engulf the prey head first until the entire animal disappears. Digestive enzymes then break down the meal over days or weeks. During digestion, the python is sluggish and vulnerable, but its cryptic coloration and habit of seeking deep cover minimize predation risk. This hunting strategy works brilliantly in Florida. Native prey species have no evolutionary experience with large, constricting snakes. They don't recognize pythons as threats until it's too late. Deer, raccoons, birds all approach within striking distance without the wariness they'd show toward a stalking panther or a lurking alligator. By the time they detect the python, they're already in its coils. The element of surprise, combined with the speed and power of the strike, makes escape nearly impossible. This is why pythons decimated prey populations so quickly. They weren't just another predator, they were an invisible predator, one against which native animals had zero adaptive defenses. For years, this seemed insurmountable. How do you control an animal that's nearly undetectable, reproduces prolifically, survives on infrequent meals, and has no natural enemies? Traditional wildlife management tools failed. Trapping doesn't work at scale because you can't predict where pythons will be. Poisoning is non-selective and environmentally catastrophic. Hunting requires enormous effort for minimal returns. Trained dogs can detect pythons, but even with canine assistance, removal rates remained low relative to population size. Biological control, introducing a predator or disease specific to pythons, was too risky given the history of biological control disasters. Every avenue seemed blocked. But the assumption that pythons had no natural enemies was about to be challenged. Something in Florida was learning to hunt them. And that something was doing it with a precision and efficiency that no human removal program had achieved. Python removal in Florida occurs through multiple overlapping programs, each with different goals, methods, and participants. Scientific research harvesting focuses on population monitoring, demographic studies, and ecological impact assessment. Universities, federal agencies, and state wildlife organizations conduct field surveys, often using radio telemetry to track individual pythons. Captured snakes are euthanized humanely, necropsied, and examined for gut contents, parasites, reproductive status, and genetic samples. This work generates the data that informs management decisions and tracks invasion dynamics. Researchers also test experimental removal techniques, including pheromone traps, trained detection dogs, and drone-based thermal imaging, though none have yet proved cost-effective at scale. The state-sponsored removal programs are more aggressive and public-facing. Florida's Python Elimination Program employs trained contractors who spend thousands of hours searching known python habitat. These individuals, often called python hunters, patrol roads, levees, and accessible wetlands, primarily at night when pythons are active and more visible. They use spotlights, thermal cameras, and GPS to locate snakes. Upon finding a python, they capture it by hand or with specialized tools, then euthanize it according to approved protocols. The program pays per snake, with bonuses for larger individuals and for females, which have greater reproductive impact. Since its inception, the program has removed thousands of pythons, but even its organizers acknowledge this barely impacts the overall population. The pythons reproduce faster than they can be removed.
Public hunts add another layer. The Florida Python Challenge, held periodically, invites civilians to register and hunt pythons over a set period, usually 10 days. Participants compete for prizes based on number and size of snakes captured. These events generate media attention, raise public awareness, and engage communities in invasive species management. They also remove additional pythons, though again the total impact on population is limited. Critics argue these hunts are more spectacle than solution, while proponents counter that any removal is beneficial and that public engagement has value beyond raw numbers. Commercial harvesting represents a more controversial approach. Some entrepreneurs have attempted to develop markets for python products, including meat, skin, and leather. The logic is that creating economic value from pythons incentivizes removal. However, markets remain small, and the effort required to harvest, process, and sell python products often exceeds the return. Regulations also complicate commercial use. Python meat must meet food safety standards, skins require processing infrastructure, and the fundamental problem remains that pythons are so difficult to find that commercial harvesting at scale isn't economically viable. Unlike alligator farming, which is sustainable because alligators are farmed in controlled environments, wild python harvesting is labor-intensive and low-yield. Ethical debates surround all these methods. Euthanasia protocols are carefully regulated to minimize suffering, but dispatching large, powerful constrictors humanely in field conditions isn't always straightforward. Approved methods include penetrating captive bolt devices and firearms, both requiring training and precision. Some animal rights advocates oppose all killing, arguing for non-lethal alternatives like sterilization or relocation, though these approaches are logistically impossible given population size and the lack of suitable relocation sites. Others argue that because pythons are invasive and causing massive ecological harm, removal is not just justified but obligated. The consensus among wildlife managers is that lethal removal is necessary, though debate continues about methods and scale. And amidst all this human effort, nature was quietly writing its own removal program. The decapitated pythons represented something unprecedented, and when scientists finally pieced together what was happening, it forced a complete re-examination of the invasion's trajectory. The answer came from multiple lines of evidence. First, careful examination of the wounds. The decapitations weren't clean cuts, not like a blade would make. They were ragged but consistent, showing crushing and tearing in a specific pattern. Forensic analysis of the bite marks revealed powerful jaws with interlocking teeth designed to grip and sever. Second, the locations. The dead pythons were found near water, often on levees, roads, or open ground where two animals might encounter each other. Third, field observations. Wildlife cameras placed in python-dense areas captured interactions that had previously gone unnoticed. And finally, necropsy evidence from live animals that had clearly survived attacks, bearing scars and healing wounds that matched the fatal injuries seen on decapitated carcasses. The culprit was alligators. But not just any alligators. Large, mature American alligators, specifically those that had apparently developed a specialized hunting strategy for killing pythons. This was the detail that shocked scientists. Alligators and pythons had been coexisting in Florida for 2 decades. Early in the invasion, interactions were documented but rare, and often ended in stalemate or mutual mortality. Famous photographs circulated showing a python that had burst open after swallowing an alligator, both animals dead. These encounters seemed to suggest that neither species was clearly dominant, that they were mismatched opponents, roughly equal in danger to each other. But ecosystems adapt. predators learn, and over time, individual alligators in python-dense areas began modifying their behavior. Instead of attempting to consume pythons whole or engaging in prolonged struggles, some alligators developed a targeted killing strategy. They would ambush pythons near water, strike at the head and neck, and use their immense bite force to sever the spinal column and decapitate or nearly decapitate the snake. The alligator wouldn't eat the python afterward. It would simply kill it and leave. This was predator behavior, but not typical predation. It was more akin to threat elimination or territorial defense. Why did this shock scientists? Because it represented learned behavior spreading through an alligator population in response to an environmental change. Alligators aren't typically considered cognitively flexible in this way. They're ambush predators with relatively stereotyped hunting patterns. The idea that they would develop and transmit a novel killing technique specifically targeting an invasive species was unexpected. Even more surprising was the efficiency. Estimates suggested that in some areas, alligators were killing pythons at rates comparable to or exceeding human removal programs, and doing so in habitats where humans couldn't effectively operate.
Further research revealed nuance. Not all alligators were killing pythons. The behavior appeared concentrated among larger individuals, particularly males over 10 feet in length. These were the animals with sufficient size and strength to overpower even large pythons. Smaller alligators still fell prey to pythons or avoided them. Additionally, the behavior varied geographically. In some regions, alligator predation on pythons was common. In others, it was rare or absent. This patchiness suggested cultural transmission, with successful hunters possibly influencing nearby individuals, or it reflected local ecological conditions that favored certain interactions. The mechanism made sense from a resource competition standpoint. Alligators and pythons eat similar prey. Both are apex predators. Both occupy similar habitats. In areas where pythons had depleted mammal populations, alligators may have faced increased food competition. Killing pythons could reduce competition even if the alligator didn't consume the snake. Alternatively, alligators might simply perceive pythons as threats to their territories or nests. Female alligators are fiercely protective of nesting sites, and pythons have been documented raiding alligator nests to eat eggs. An alligator that kills pythons near its nest could increase offspring survival. The discovery had immediate implications. It meant that Florida's ecosystem possessed a latent resistance mechanism that was only now manifesting. Alligators, a species that had itself been nearly extirpated by hunting in the mid-20th century but recovered due to conservation efforts, were now serving as a biological control agent against an invasive species. This was nature adapting in real time, and it happened without human intervention, without planning, purely through ecological pressures selecting for individuals and behaviors that reduced python success. But questions remained. Would alligator predation be sufficient to control python populations? Probably not alone. Python reproductive rates are too high, and alligators can't access all python habitat.
However, alligator predation could suppress python numbers in certain key areas, particularly around waterways and in wetlands where both species overlap most heavily. This could create refugia where native prey species persist, allowing some population recovery and maintaining biodiversity that might otherwise be lost. Additionally, if alligator predation selectively targets larger pythons, which are the primary breeders and biggest consumers of prey, the demographic impact could be disproportionately beneficial. The discovery also changed management strategies. Instead of viewing the Everglades as a system in total collapse, managers now had evidence that native species were mounting a counteroffensive. This didn't mean humans could stop removal efforts. It meant that human efforts could be strategically coordinated with natural predation to maximize impact. For instance, protecting alligator populations and habitats became even more critical. Ensuring healthy alligator densities in python-infested areas could amplify control effects. Research into what conditions favor alligator predation on pythons could inform habitat management decisions. Moreover, the finding opened questions about other potential native responses. Were other predators also adapting? Were there behavioral changes in prey species that increased survival? Was the ecosystem finding equilibrium at a new, python-inclusive stable state, or was this the beginning of a slow recovery? Scientists began looking more carefully at long-term trend data, searching for signs that the worst ecological impacts had plateaued or were beginning to reverse. Some evidence suggested that in areas with the longest python presence, certain prey populations had stopped declining and might be stabilizing at low but persistent levels. Whether this represents true adaptation or simply the survival of remnant populations in python-low microhabitats remains under investigation.